Welcome back everyone. Today we will talk about extractive distillation technique, and first of all let's have some background information related to this technique. We all know that the isotopic mixtures pose some difficulty for separation, and there are different techniques to break the isotope and to separate the isotopic mixture, such as pressure swing distillation. And another technique is the extractive distillation. In this technique, we add a third component apart from the separating main component, which is actually a miscible and have a high boiling point and relatively non-volatile component, and we called it as a solvent or as a entrainer in extractive distillation terms. And this newly added component should not form any isotrope with any other component in the mixture. So this technique is called extractive distillation, and usually this method is used for the mixtures which have a very low relative volatility value. For example, the mixtures which have a very close boiling point with each other. For the example of these kind of mixtures are ethanol and benzene. You can see in this table the boiling point temperature of ethanol and benzene are very close to each other. So if we want to separate ethanol and benzene without any addition of third component, so it's almost very difficult to separate in just one distillation column. So what we do, we add a third component with a relatively high boiling temperature. So the addition of this third component will change the isovolatility of one component with respect to the other component. So this is just a very simple basic information regarding extractive distillation. So let's go to the learning objective of this tutorial. Today you will learn how to use a cape open distillation column exported from the ChemSep software into DWSIM software. And then you will learn how to use a recycle logical operation, and finally we will simulate extractive distillation problem. So today's problem, I took it from a research article, and I am citing the research article here. It's the determination of an optimum entrainer for extractive distillation based on isovolatility curve at different pressure. So for comparison and for further reading, you can go to this article and check your result and compare it. So this is the flow sheet that we will develop in DWSIM. We have an isotopic mixture consisting of ethanol and benzene. So ethanol and benzene at 25 degrees C, and the flow rate is 100 kg per hour, and it is fed into the distillation column on the stage of 50, and the total number of stages are 71 with reflux ratio of 2.13. On the other hand, the entrainer or the solvent with makeup and recycle stream are fed on stage number 24. We have to find out in first extractive distillation column how much is the mole fraction of ethanol in the top product, and in bottom the mole fraction of benzene is given, that is 0.189, and the bottom mixture is fed to the second distillation column, that is called solvent recovery column, and this column has total 21 number of stages including the condenser, and the reflux ratio is set here 6.14, and feed enter on stage number 8. And we have to find out the benzene mole fraction at top, and the bottom product bottom molar product flow rate is given, that is 214.7 kilomole per hour. So the bottom product pass through a cooler, and the cooler outlet temperature is 323.15 Kelvin, and this stream is recycled and mixed with the makeup stream and fed again into the distillation column, extractive distillation column. So this is the flow sheet that we are going to develop in DWSIM. Let's move to the DWSIM software. Well, we are already in DWSIM software environment, so just create a new steady state simulation. So the first step is define component. So we have three component: ethanol, benzene, and the last one is p-Xylene. So just add these, and after that just check. So just go to the next step and select thermodynamic property package, and for this problem we will use edu.X as a fluid package, and then go to the next step and select the system of units. I will clone the system international unit and will change, for example, the molar flow rate we have kg mole per hour, mass flow rate we have kg per hour, and the rest of the things, maybe the pressure is atm and temperature is Kelvin. So everything seems fine, so just press finish. So now we are ready to go for our flow sheet construction. So just take material stream and put it into the canvas. Take another one, take a mixture and put it here. Okay, so just left click on it and rename it is feed. And we know that I just forgot to tell you one thing, that the whole system is operating at a constant pressure. We are not considering any pressure drop here, so everywhere pressure is 1 atm. Okay, so in feed, so the temperature and pressure are already set. We just have to change the molar flow rate and then go to the compound amounts. Ethanol is 0.5 mole fraction, benzene is 0.5 mole fraction, p-Xylene is 0, and then just press accept changes. Similarly, the second stream, this one material stream 2, we can change it makeup stream, and the temperature pressure are okay, and here the molar flow rate is 0.301 kmol per hour, and go to the composition here, change it, it's ethanol is 0, benzene is 0, and p-Xylene is 1. Just press accept changes. Okay, so just make up stream. Okay, so here I would recommend you to just pause your solver, otherwise it will delay the flow sheet making process, because when I enter anything it will start to calculate. Okay, so I am just going to disable the flow sheet solver. Okay, now after that just right click on this mixture and rotate it into 90°, bring it here and connect it with the makeup stream and generate another stream, and also the outlet stream. Okay, so and right click on it and rotate it again 90°, so it looks better. Okay, and change the material streams 3 into the name of solvent, and this one I can say S1 because it's entering into the first distillation column. Okay, and after that just from unit operation ribbon, go to the cape open and select cape open operation and drop it into the simulation environment, and it says ChemSep column flash. Yes, we want to introduce from ChemSep software. Just left click on it, and after that on this left side ribbon, go to the open cape open project cape open object editor. So left click on it and wait a bit. So the first column is kind of a complex, and total number of stages are 71. It's given in the flow sheet, and rest things seems okay. Okay, so here we have to select define the type of operation. For example, the column is complex condenser. We are going to have a total liquid product, in reboiler partial liquid product, and you can see here there are two feed. One is entering at plate number 50, another one is on plate number 24. So we have to define here two feed entrance. So the first one is 50 and the second one is 24. I'm just pressing enter, so you can see here there are two feed ports have been generated. After generating these two feed stream, just cross this one and save the information that you insert, and then again go to the left side of this window and connect the feed stream. So the feed one, that is the main feed, will connect to the stage number 50, and the S1, that is the recovered solvent or recycled solvent, will be connected on the stage number 24. After that, go to the outlet connection and create two outlet connections by clicking on this C button. So the number 5 is top, number 6 is bottom. So here I can change its name into ethanol because we want to recover ethanol from here, and here we are going to change it B1 bottom product. Okay, so again just left click on it, again open cape open object editor. Okay, now you have to specify the thermodynamics because we are not going to use the ChemSep thermodynamic, but we will want to give our own specific values for this problem. So the thermodynamic for K values, we will choose decema, and for activity coefficients, as we already choose UNIQUAC in main flow sheet, so we will use the same. For vapor pressure calculation, we will use Antoine equation, and for enthalpy, we will select the ideal. Okay, after that go to the specification, and because we are solving this problem as a constant pressure, there is no pressure drop, so the top pressure and the condenser pressure will be the equal. After that go to the column specification, and for top we are going to specify the reflux ratio. For the first column, reflux ratio is 2.13, so we will add here 2.13 and press enter. For bottom, we have to specify a mole fraction of a component, and the component is benzene, and the mole fraction is 0.189 in the bottom. Okay, 0.189, then just press enter. So all the input streams have been selected. You can see everything is green, only the results are red. When we simulate the flow sheet, the results will be available. After that, just close this window and press yes. We want to save all these changes. Next step is to add second column. Okay, so again click on it, go to the left side of this window and open the Cape Open Object Editor for the second column. And this one is total number of stages are here 21, and the distillation is simple distillation because we are going to separate solvent, and there are only kind of two components mainly, because most of the ethanol will be recovered in the first column. Okay, so after that, and you press OK. So what you have to do first, let's first connect the inputs and outlet streams. For that, go to again this left window after left clicking on the second column, and in feed just connect B1 as a feed, and the outlets just generate two outlets by clicking on this create stream, create bottom stream. So the top stream is number 7 and the bottom stream is the number 8. Okay, so just let's change the name. Material stream 7 is mainly consisted benzene. Okay, and the material stream sorry, I did not enter the name, so it's benzene. And the material stream 8, it will mainly consist of p-Xylene after writing the name. So now if you go to the flow sheet, after this bottom product, it must have to pass through a cooler, and the outlet of the temperature will be 223.15. Okay, so just before going further, I just want to finish the specification of the second column. So for that, just left click on it, open Cape Open Object Editor, and after that go to the operation. It's equilibrium column, simple distillation, we want total liquid product, and from reboiler we also want total liquid product because we are going to recycle it again. Total number of stages are 21, and the feed stage is by default is selected 10, but in problem statement it's said that it should be on feed number stage number 8. So just change it here, instead of 10 just press 8. Okay, after that go to the thermodynamics, and again you have to specify Dechima, and activity coefficient will be unique-Q, and vapor pressure in Toin, and enthalpy we are just taking known. And now go to the column specification, and the top product name, and the top specification is again reflux ratio, and for second column reflux ratio is 6.14. okay, so just write here 6.14. okay, and for bottom product for bottom specification we have a bottom product flow rate in kg mole per second here, and in flow sheet we have kg mole per hour. Okay, so I just uh, change it in from kg mole per hour to kg mole k mole per second, that is equal to 0.05968. okay, after that just press enter, and now all the specification for second column has been given. Everything is green, only results are red. Okay, just close this window and save all the changes that you have made. Okay, so next step is introduce the cooler. Just go to the exchangers and drag and drop cooler here, and left click on it and connect inlet stream as a p-Xylene, and create outlet stream, create energy stream. Okay, and the outlet stream, just left right click and invert horizontally so it looks beautiful in the flow sheet. Again just click on the cooler, left click, and from here left side this menu, you just have to change what we want with this cooler. So we actually want to specify the outlet temperature, and the outlet temperature should be 223. So just change here 323 and press enter. Okay, now the cooler is specified. Next we have to introduce a logical operation, that is the recycle block, and put it here. Left click on it, and as a inlet, material stream 9 is the inlet of recycle, and the solvent stream is the outlet. Okay, so right click on it and invert horizontally. So now you can see it seems beautiful, and the flow sheet is almost complete. Okay, so we specify first column, we specify second column, we specify the cooler outlet temperature, and we specify feed. Sorry, I have to specify it again because it's 100 k mole, and the composition is fine. Again check the makeup stream. Again it was sorry, 0.301. Press enter. Okay, and the solvent. So to run the simulation we have to take an initial guess to start the recycle loop, because we know that the bottom product of second column mainly consisted on p-Xylene, and we know the bottom product flow rate. So the recycle stream flow rate more or less would be close to this this flow rate, and we will not know the composition. Okay, but as an initial guess, what we will do, we will take ethanol 0 in recycle stream, benzene 0, and p-Xylene 1. Okay, so after just accept changes and stream condition, the molar flow rate for initial gas we will take it around 200 kmol per hour. Okay, now everything is set, so let's simulate this flow sheet. Just activate the flow sheet solver and press F5, and now you can see the flow sheet is being solved. So now the flow sheet has been converged. The next step is to check the results. For that, what I will do, just go to the stop ribbon and select master property table. Okay, so double click on, maybe I just arrange the flow sheet a little bit. So double click on this, and what are our main interesting streams? So the feed, makeup, solvent, we want to know ethanol, we want to know benzene, and finally we want to know p-Xylene. And maybe makeup and feed, we already know their specification, so we are more interested in results, the results produced by the software. Okay, what we want to know: molar flow rate, okay, and mole fraction mixture ethanol, mole fraction mixture benzene, so mole fraction mixture of p-Xylene. So these are some main parameters that we want to know. Okay, just close this one, and now here you have final results. So the solvent molar flow rate is 201.14 kmol per hour, and in solvent, no ethanol. Solvent stream, you know what, where is it? If we can see the simulation, this one is the solvent stream, that is actually the recycle stream. And in p-Xylene stream, that is here, the bottom of the second column, it has mainly p-Xylene, almost 97%, and the ethanol, that is the top product, top stream of this first column, it has 96% of ethanol. And the second column is the top product of second column is benzene, that has 99.99% mole fraction of benzene. So for better understanding and comparison of your results, with you want to clarify that if they are correct or not, just go to this research article and read it and compare your result with that, and in this way you will learn a lot. For today's tutorial, that's enough. I hope you understand it and you like it. So please don't forget to subscribe and like my channel and share it. Thank you very much, and see you next time. Bye bye.